Okay then, so now we have the Oneida lemma under our belt, we're really in a very good position to be able to understand lots and lots of things that are going on in this category of functors from C to set. So thinking once again in the general case, let's now start to explore some different kinds of ideas to do with limits and co-limits. And a really nice place to start is with the idea of products, okay? Because products are just so important, um, especially if you're interested in things to do with topos theory. Like, products are just used all the time, so it's very important to understand what the kind of product of a pair of objects A and B in this category set to the power of C is going to be. So let's consider this. Suppose we have a functor A from C to set and a functor B from C to set. We're thinking of these as objects in set to the power of C, and we want to compute the product of them. So we know that such products exist because we know that set to the power of C is a topos, or at least I tell you that it is. In fact, if you follow this video through to the end, you'll basically have seen the proof that it's a topos, because we're going to show how to construct all of the different gizmos that we're required to be present in a topos. But yes, products do exist. So how do we compute them? Well, of course, we have to start by recalling the definition of the categorical product of objects A and B, and that is an object we call A times B with arrows P1 into A and P2 into B. These are called projections. And it has to be such that for any similar kind of thing, so for any arrow Y with an arrow F into A and an arrow G into B, there's this unique arrow that we call F comma G in angle brackets that makes this diagram commute, okay, in the sense that P1 after F comma G equals F, and P2 after F comma G equals G, okay? So that's just the definition of a categorical product, and really the important thing is it gives us this sort of correspondence here, that if we have a pair of arrows, F and G, that if we have an arrow F from Y to A and an arrow G from Y to B, then that corresponds with an arrow F comma G from Y to A times B. And we get this arrow F comma G here just by sort of invoking the sort of definition of a categorical product, this kind of universal property that there has to exist this unique intermediary arrow that makes this diagram commute. And we can go the other way around as well. If we have an arrow from Y to A times B, then if we do P1 after it, we get an arrow from Y to A, and if we do P2 after it, we get an arrow from Y to B. So we can go from an arrow into the product to a kind of pair of arrows, one into each of the things involved in the product. So that's just the definition of the categorical product. But this is very nice because it's basically talking about what happens to do with arrows into the product. And we now know how to talk about, basically we know how to talk about the kind of E-type elements of A times B in terms of arrows into A times B. That is arrows from these Hom functors, or if you like, a natural transformation, or if you like, natural transformations from, say, Hom E comma blank to A times B. And so we can basically mix these things together to get a very succinct kind of reason why so we can basically mix these things together to get a very, very informative kind of description of what's going on with the product of objects in set to the power of C. So here's the argument then. For an object E in our category C, we have these following kind of correspondences. Let's say we have an E-type element theta of our object A and an E-type element phi of our object B. Well, if we sort of apply the Yoneeda correspondence, we can convert those into an arrow theta under arrow from hom e comma blank to a, and an arrow phi under arrow from hom e comma blank to b. And now if we apply the kind of correspondence that comes about by this thing being the product of a and b, we see that having this kind of pair of arrows, an arrow from hom e comma blank to a and an arrow from hom e comma blank to b, such a pair will correspond to this kind of intermediary arrow, this arrow represented by these angle brackets, and this is going to be an arrow hom e comma, and this is going to be an arrow which is called open angle bracket, and this is going to be an arrow which we can call theta under arrow comma phi under arrow, and this is going to be the kind of arrow from hom e comma blank to a times b. So this sort of appearance of this kind of producty pair arrow is just the same as this kind of idea I've written in purple, just when y here is a hom functor, okay? And then what we can then do is we can say, aha, I have an arrow from hom e comma blank into a times b, so I can kind of go the other way with the Yoneeda correspondence, and I can then sort of find the sort of E-type element of a times b that this arrow corresponds with, and that's just going to be an element of the set a times b of E, and we call that element theta comma phi in round brackets, okay? So each of these horizontal lines here represents an isomorphism, and so we can convert either way between these two things. So we can essentially think of the E-type elements of a times b as pairs, a kind of E-type element of, so we can basically think of the kind of elements of a times b of E as pairs, an element of a of E paired with an element of b of E. And we can go from, such a element of the product, and so we can go from such an E-type element of the product to a kind of pair of E-type elements, one from A of E and one from B of E, or we can go the other way around as well. We can go from a pair, or we can go the other way around as well. We can go from an E-type element of A and an E-type element of B to a E-type element of A times B. And so if you want to think of this kind of thing set theoretically, you could basically just say, well, the set of E-type elements of A times B is just the set of pairs theta comma phi, such that theta is in A of E and phi is in B of E. Or if you want to write it in an even simpler way, you could just say that this is just the Cartesian product of the set A of E with the set B of E. So we see that basically the way that products work in set to the power of C is pretty similar to the way that products work in the category of sets. It's just that we have sort of multiple types of elements, but the way it works on anything of a particular type is pretty much the same as it works in sets. And indeed, all kind of limits and co-limits have this sort of feature. They're not really much more complicated in set to the power of C than they are in set. But I want to carry on going through the details because it's just very sort of interesting to see how all of the kind of features related to the categorical product just sort of fall out once we have this Yoneeda, once we have all these results related to the Yoneeda lemma that I've already gone through. So here's another one then. We kind of have already argued basically what the structure of this set A times B of E should be. So we basically know what the E-type elements are of this product, but we don't know how the S action works on them yet. So we can get at that in quite a straightforward manner just by kind of applying our action lemma. Okay, so suppose we have an arrow S from E to V in the category C, and so we want to do this S action on our pair theta comma phi of E-type elements of A times B. So basically we want to compute A times B of S of theta comma phi. But actually, let's look at the kind of natural transformation corresponding to that, because then we can exploit results we've already got related to the Oneida lemma. So we want to compute this kind of natural transformation corresponding to this element here. So this is an element we're getting by doing an S action on the E-type element theta comma phi. So this is supposedly going to be a V-type element of A times B, and we're looking for the natural transformation that's going to correspond with that. And so we can apply our action lemma, and so we know that this is just going to be equal to theta comma phi under arrow after HS. And we already know that the kind of natural transformation corresponding to theta comma phi, as is indicated here, is just going to be theta under arrow comma phi under arrow. Okay, this arrow from hom E comma blank to A times B. So we can rewrite this whole thing here as theta under arrow comma phi under arrow all after HS. And then we can bring the HS inside the angle brackets as usual with the categorical product and rewrite this as theta under arrow after HS, comma phi under arrow after HS. And now what we can do is we can apply the action lemma again, sort of the other way around now. So we know now that, again, using the action lemma, we know that theta under arrow after HS is just going to be A of S of theta is just going to be the natural transformation corresponding to AS of theta. And similarly, phi under arrow after HS is the natural transformation corresponding to B of S of theta of phi. And similarly, we have that phi under arrow after HS is just going to be the natural transformation corresponding to B of S of phi. So the important thing then is that this thing that we started with is equal to this bottom purple line here. And this is basically saying that this natural transformation is equal to this natural transformation. But if we sort of, again, use our Oneida correspondence, we can think, well, let's just talk about the kind of element corresponding to this natural transformation. And that would basically just involve sort of rubbing out this underneath arrow in our notation. And then that's going to correspond with the sort of so basically what we've shown here is that this purple expression here that we started with, this natural transformation, is equal to this purple expression at the bottom here, this other natural transformation. But let's just convert these two things back into elements. Okay, so we'll use the kind of Oneida correspondence again. So that allows us to just sort of delete this arrow here in this top purple expression, because we're talking about the kind of elements that this is going to correspond with, the sort of V-type element of A times B that this thing corresponds with. And that's, of course, got to be equal to the sort of V-type element that this expression in purple at the bottom corresponds with. And that's just going to be AS of theta, comma, BS of phi. Because we see here that when we have two kind of because as we see here, we can sort of define theta comma phi in round brackets, this E-type element of A times B, as the sort of element, as the sort of E-type element of A times B corresponding to theta under arrow comma phi under arrow. And in a similar way, the sort of V-type element of A times B corresponding to A of S of theta under arrow, comma B of S of phi under arrow is just going to be A of S of theta, comma B of S of phi. Okay, so we have this result. And this is basically what we're after, because it really tells us in a kind of element-wise way how doing the S action works. And it's not really much of a surprise because it's just basically the same. And it's not really much of a surprise. It's about as simple as it could be. The idea is that the E-type elements of A times B are just like pairs, theta comma phi. And if we want to do an S action on such a pair, well, we just do the S action on theta in A, and we just do the S action on phi in B, because phi lives in B. Okay? So we've basically seen now what the main structure of these products is. So let's just have a quick glance at what products look like in this category of functions, which we're sort of focusing on. So here I'm just sketching the product of this bouquet A with this bouquet B. And it's fairly easy to kind of graphically calculate these things. If we just set the things up as if we're kind of making a table or something, then we basically just have that the set of vertices of A times B is just the set of pairs of a vertex of A paired with a vertex of B. Similarly for the loops of A times B basically equal to the Cartesian product of the set of loops of A with the set of loops of B. And we also have this sort of fairly expected result that if we have a loop, in the product, let's say C comma B dash, for example, and we want to work out what the vertex of that loop is, well, we simply ask what's the vertex of loop C in A, and what's the vertex of loop B dash in capital B. And then we just get those two results. So in this case, 2 and 1 dash, and then that pair is going to be the vertex of A times B, which is going to be the vertex of this loop C comma B dash. Okay, so this is all fairly, it would be difficult to think of a simpler kind of state of affairs than this, really. So this is all really sort of what you'd probably imagine. And then the other result is sort of how the projections work, which I'm about to get onto, but you can basically see from the picture how the projections work. Just imagine sort of collapsing down this picture, just taking the first components of these kind of elements here in this product, which are all sort of pairs, and you see that, for example, vertex 1 comma 1 dash is going to get projected to become 1, and for example, this loop C comma B dash under the first projection P1, that's just going to get sent to C, and so on. So P1 sends all of these pairs to their first entries, and P2 sends the pairs to their second entries. So that's basically it. So that's basically it. But let's see how the projection works a bit more systematically, just because it's interesting to see how all these kind of results fall out kind of mechanically. Now we've got all of these things in place. So we're interested in understanding the nature of this arrow P1, this projection from A times B to A. So let's ask ourselves a question. What does the ETH component of P1 do to our E-type element theta comma phi of A times B? Well, actually, let's ask what's the natural transformation corresponding to that. And then we can apply our natural lemma to say that this is going to be equal to P1 after theta comma phi under arrow, and we know that theta comma phi under arrow, that's the natural transformation corresponding to theta comma phi, and we know that's just going to be theta under arrow comma phi under arrow. We saw this kind of correspondence here. So we have that P1 after theta comma phi under arrow is equal to P1 after theta under arrow comma phi under arrow. And then we know how P1 works in one of these, and we know what happens when we do P1 after one of these kind of producty pair arrows with the angle brackets. It just takes the first thing from the pair inside the angle brackets. So the result of this is just going to be theta under arrow. And so basically, if we look at this, we've basically argued that this natural transformation we started with is equal to theta under arrow. So if we just sort of apply the Yoneeda correspondence again, then we get the kind of element-wise situation, which is just that doing the ETH component of P1 on theta comma phi just gives us theta, okay? And of course, similarly for the second projection, doing the ETH component of P2 on theta comma phi just gives us phi. So it's pretty simple how the projections work. Again, it's basically just like what's happening in the category of sets. And then just to complete the kind of understanding of the categorical product, let's understand how these kind of producty pair arrows like this F comma G drawn in green, how these behave in general, okay? So, you know, suppose in our category, we actually, so, you know, suppose in our category set to the power of C for a general C, we actually compute A times B. But then, you know, we have a situation where we have another object Y, and we have an arrow F from Y to A, and an arrow G from Y to B. And then we know that there ought to exist this unique arrow F comma G, which makes this diagram commute. But how do we actually get this arrow? How does it work? I mean, it's really going to be a natural transformation from the functor Y to the functor A times B. So how do we get at it? Well, again, we can just sort of apply our previous results. So let's think about the kind of ETH components of this natural transformation F comma G. and that's just going to be a function from y of e to a times b of e. And so let's think about how that function works on a element theta of y of e. Okay, so we're really interested in what happens when we do the ETH component of f comma g on theta, but and that's going to be and that's going to give us an E-type element of a times b. But we want to use these kind of connections with the Yoneda lemma. So rather than talking about that element, let's talk about the kind of natural transformation that corresponds with, because now we can apply our natural lemma again, and we know that this is going to be equal to just f comma g after theta under arrow. And we can just rewrite that, taking this theta under arrow inside the angle brackets. We can rewrite this as f after theta under arrow, comma g after theta under arrow. And then again, using our natural lemma, we can rewrite this as f subscript e of theta. And then again, using our kind of natural lemma, we can rewrite this as the kind of producty pair of the natural transformation corresponding to f subscript e of theta with the natural transformation corresponding to g subscript e of theta. And so it's the same story we've seen before. Basically, we're saying that this red natural transformation we started with is equal to this red natural transformation down here. So let's now convert these things back into elements using the Yoneda correspondence. So this top thing just becomes f comma g subscript e of theta, and this bottom thing just becomes f subscript e of theta comma g subscript e of theta. So it's pretty simple then how f comma. So then okay, now we can really understand how f comma g works. Basically, it's going to be a natural transformation from y to a times b, and its ETH component is just going to take an E-type element of y, an element theta, and it's just going to form this kind of pair, this kind of element of a times b of e, this pair f subscript e of theta comma g subscript e of theta, which is basically again just the same way that these kind of intermediary arrows work when we're talking about products in the category of sets. It's just now we might have sort of several different types of elements in these kind of collections of structured sets which form the kind of objects in set to the power of c. But anyway, they're the details. Let's have another look at an example. So as I say, we're really interested in this kind of example here, where we're looking at this category. So as I say, we're really interested in looking at these examples here, and in particular, this case where we're looking at this category of functions. So we can illustrate A here as this bouquet and B here as this bouquet. And then, as I've already said, we can basically form the product kind of graphically. So the important things when you actually want to sort of draw out a product is you sort of basically have a look at this result here, which really tells us what the kind of E-type elements of A times B are. And so basically, So basically the key to this is that you can use this kind of result here, and this sort of tells you what the E-type elements of A times B is. It's just the sort of Cartesian product of a set of A-type elements. So, okay, basically the key then to sort of doing this type of construction and actually being able to picture what the product of two objects in this kind of category is firstly this idea up here that the kind of set of E-type elements of A times B is basically just the Cartesian product of the E-type elements of A with the E-type elements of B. So we can use this like we are doing here. For example, the kind of set of vertices of A times B is just the set of pairs of a vertex of A paired with a vertex of B, and similarly with the loops. So that tells us kind of what the things are in A times B. And then the other thing we need to know is how are they stuck together? In other words, how does the S action work on these different sorts of elements? And for that, and to understand that, we just use this kind of result here, okay, which basically says that if we want to do an S action on a kind of pair element theta comma phi in A times B, then we can just do the S action on theta and then pair that with the thing we get from doing the S action on phi. So it's pretty simple to see how this works in this case of bouquets. So basically all it's saying in the case of bouquets is that if we have a loop in the product, then that loop's going to be indexed by a kind of pair, a loop from A paired with a loop from B. And if we just do the S action on that first entry in the pair and see what we get in A, well, in this case we get 2. And then if we do the S action on the second entry, that'll be an S action in B, which in this case will give us a 1 dash. So we just pair those two results together and we get 2, 1 dash. So that will be the vertex of this loop here. Okay. So this is basically how we can work out what the S action does to a kind of element, an E-type element of A times B. And this basically allows us to be able to actually draw out these kind of things. Now, it's, you know, when we now we come to a point here where there's, now I really think that now I just want to step back here and say something, which is that we are really in a very fortunate position looking at these kind of systems with this kind of language, because we have so many different ways to say the same thing. We have like several different ways to talk about products. We have ways to talk about things in terms of elements. We have ways to talk about things in terms of arrows. We have ways of representing these kind of objects in our category of functions. We can think of them as functions. We can think of them as bouquets. We can think of them as functors. And so we have all of these different sorts of viewpoints that we can take on things. And this is so cool because it allows us to, you know, that paired with the fact that all of these different perspectives can all be kind of obtained. We don't have to do any particularly hard calculations in order to be able to sort of look at things from these different perspectives. So it's so worthwhile to just think, well, how does this situation look if we take a kind of different perspective? And in particular, this picture here I'm drawing is basically what the product of A and B looks like when we draw it as a bouquet. And okay, we see what it looks like, and this picture yields a bit of intuition. We see how we can draw this as a sort of rectangle, and it looks like a sort of multiplication table or something. And we can see sort of there's ideas reminiscent of the notions of categorical products and setting things up in rectangles to represent products of things. We can glean some intuition from this. We can also see how the projections work. So, for example, how does P1 work here? Well, it's going to send C comma A dash to C. It's going to send C comma B dash to C. It's going to send A comma A dash to A comma B dash to A, B comma A dash to B. So we're just selecting the first components of each of these pairs. And similarly for the vertices, 1 comma 1 dash gets sent to 1. 2 comma 1 dash gets sent to 2, etc. It's very simple, really. P1 here is just sending everything downwards. P2 here is sending everything to the left, etc. But, just because we have one good viewpoint of how the sort of product of a couple of objects in this category of functions looks like, doesn't mean we should stop there. I mean, we had another way of visualizing objects in this category of functions, and that was just literally as functions. So what does the situation look like here? Well, you see, basically I've just drawn out an example here. So we have this function AS from AE to AV, and this function BS from BE to BV. And so I've drawn the functions here, and then this is a kind of picture of the product. And it's this same case we've already calculated, okay? And you could say, so what? Maybe this looks more complicated to you than this picture here with the bouquets. But it's quite interesting to draw things out this way because you start to notice things. So, for example, like the essence of this object we're really after is this kind of function here that we're calling A times B of S. And this is a function from A times B of E to A times B of V. But we also know that we can write this really as the kind of, if we want to think of it as a set, we can think of it as a sort of Cartesian product of A of E with B of E. And similarly, we could write this as the Cartesian product of A of V with B of V. Well, so what, you might ask? Well, I mean, think about it. Haven't we seen a kind of arrow that goes from a kind of product of sets to a kind of product of sets? When we were looking at the category of sets, have we seen an arrow like that before? Well, we kind of have actually, haven't we? What about this kind of situation? In fact, we have this kind of situation in a general kind of Cartesian closed category, where if we have a kind of product of objects, so in this case, we're thinking of the category of sets, and we're thinking, well, we have the product of A of E, which is just a set, with B of E, which is just another set. And we have this arrow from A of E times B of E to A of V times B of V. And we know that there is an arrow like that because we have an arrow A of S from A of E to A of V, and we have an arrow B of S from B of E to B of V. So if you want to understand what I'm saying now, just remember that we're dealing with the... So just to be clear about what I'm talking about here, what I'm saying here is that just think about this being a set, and 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 think that we're working in the category of sets, and recall that we already have a sort of definition, given that we know that in the category of sets, we know we have this arrow AS from AE to AV, and we also have this arrow B of S from B of E to B of V. And so we know from the sort of basic kind of notation that we employ when we're talking about kind of products, that we have this arrow that we can write as AS times BS. And, you know, we've talked about this kind of arrow before in previous videos, and we've said usually that it's just shorthand for AS after P1, comma, BS after P2. And all of this stuff, I must emphasize, is just things I'm talking about that's just happening in the category of sets. Okay, but isn't it interesting that we call this kind of arrow the product of AS and BS? And isn't it interesting that this arrow has exactly the same source and target as does this arrow here, which we've actually worked out as being the sort of product of this kind of function, which we called AS, and this kind of function, which we call BS. But all of this kind of calculation was done in this category of functions. When we did this calculation, we weren't really thinking of A of S and B of S as arrows. We were thinking of them really as the sort of essence of these objects, A and B, in this category of functions. And we did all this work, and we ended up with this kind of picture here. But if you look at this picture, you'll notice that actually this result which we get, A times B of S, which is really the sort of essence of the product of A and B in this category of functions, is actually exactly the same as this kind of function here, A of S times B of S, which is really what we were calling the product of functions in the category of sets. Okay, so there's a lot of kind of coinciding terminology here. So let me just sort of draw this out so I'm clear about what I'm talking about. Basically, in set, so basically just to try and simplify what I'm saying that in set we have the AS and BS and AS times BS. These are all arrows, but also in our category of functions, we have the A and B, and A times B are all objects in the category of functions. But I mean, basically, the kind of essence of A is AS, and the essence of B is kind of BS, and the essence of A times B is A times B of S. And it just turns out that these two things happen to be equal, which is really remarkable, okay? So can we see this quickly? Well, yes, we can. Remember that what we're writing in set as AS times BS was really just shorthand for AS after P1, comma BS after P2. And that was really just a function when we were working in the category of sets. It was just a function from this Cartesian product to this Cartesian product. And the way that it worked for a kind of pair of elements, theta comma phi, of A times B comma B times E, is it just sent those two, is it just sent that kind of pair of elements to the pair AS of theta comma BS of phi. But look, this is exactly the same thing as how this kind of function here works. A times B of S. Okay, it also sends this pair theta comma phi to A of S of theta comma B of S of phi. So these are exactly the same functions. Okay, we do indeed have this kind of equality here. So basically, what we find out is this remarkable result that doing the product of these objects, A and B, in this category of functions here, is basically the same thing as just sort of taking the functions, you know, which, I mean, the essence of these objects are really just A of S and B of S, and just thinking of those things as literally sort of arrows in the category set, and then just working out the product of those arrows according to our kind of previous definition of how we can work out the product of arrows in a category. And we get the same thing, which I think is truly remarkable. And, you know, I discovered this result just recently. I don't think it's particularly like earth-shattering, as far as I'm pretty sure it's already well known and all the rest of it, but it's just remarkable, like, what you can get out of just deciding to draw a picture, that it's possible to realize these things. And I mean, it can always sort of lead on more kind of avenues for investigation. For example, I really imagine that this similar kind of idea would hold if we were dealing with a more general case, like instead of dealing with sets to the power of this kind of category with an arrow from E to V, maybe we could just replace that set with a general kind of Cartesian closed category. And I imagine we'd have a kind of similar result, that if we look at the way that we can do products of arrows in this category D here instead of set, then that would end up being the same as the way that the kind of categorical product of a pair of objects in this category of functors from C to D looks, then that would end up. So basically what I'm saying is that if we, instead of looking at this sort of so basically what I'm saying is that if we call this category here, where we just have an arrow S from E to V, let's just call that the single, let's just call that the dart category, just to give it a name briefly. So basically what I'm saying is that I imagine there's a generalization of this kind of idea, which is that if we have some Cartesian closed category D, and we think about the kind of notion of taking the product of kind of arrows in D, this kind of idea that if we have an arrow F from U to V and an arrow G from X to Y, then we can form this kind of arrow F times G, which goes from U times X to V times Y, this kind of idea. Okay. I imagine we'd end up with the same kind of notion as if we think about the kind of idea about what the categorical product of objects in this category of functors from our kind of Dart category, our category with one arrow that sort of makes the category of functions in the previous case. But if I'm basically saying that if we look at that notion and then we compare it, we'll probably see that it's, so basically I conjecture then that if we then look at the notion of the categorical product of a pair of objects in this category of functors from this kind of Dart category to D, then we'll probably basically see the same idea that, finding the product of a pair of objects in this kind of category, that product will basically look the same as just finding the product of arrows in the category D. Okay, because it seems as if all the mechanics ought to work just the same way, even if we're not really working with the category set. But I mean, it's the fact that it's so easy to generalize things in category theory really makes it worthwhile to grab some nice simple examples and look at how they work explicitly, because once you see something like this working, it's pretty easy usually just to sort of find the most kind of general version of that idea, and that can lead to some very interesting category theory.